Hi class! In this lecture video, we will try to solve a problem involving a series parallel circuit. In this problem, we are asked to determine the equivalent resistance of the combination of resistors as shown below. So in the figure, we have 5 resistors connected. R sub 1, R sub 2, R sub 3, sub 4, and R sub 5. Now, if you will notice in this figure, we have both the two connection series and parallel. If we're given this kind of connection and we want to determine the equivalent resistance, we have to approach the problem such that the resistors must be combined. The equivalent resistance of such combination can be found by combining the resistors part by part until it ends up with only a series or a parallel connection. So we're going to approach this part by part. If you will look at the big picture, the circuit seems complicated. We have to make it look more simple. We have to come up with a circuit that is more that is either a series or just a parallel circuit. Okay? Notice that we have resistor R sub 4 and R sub 5. They are connected in series with each other, but they are parallel with R sub 3. Notice as well that this whole connection, so whole loop between R sub 3, among R sub 3, R sub 4, and R sub 5, they appear to be in series with R sub 1 and R sub 2. You notice that? So if I will redraw it, I could make it smaller. The idea is R sub 4 and R sub 5 seems to be in series. However, R sub 4 and R sub 5 are in parallel with R sub 3. Again, R sub 4 and R sub 5 are in series with each other, but they are in parallel with R sub 3. One more thing, from the figure, we could also see that the combination of R sub 3, R sub 4, and R sub 5, they are all in series with R sub 1 and R sub 2. So to explain this connection, I can convert this circuit into a smaller version. First, I will treat R sub 4 and R sub 5 in series with each other. So I can redraw it as this. This is the battery, the first resistor, the third resistor, the second resistor, and what I'm going to do with R sub 4 and R sub 5 is I'm going to combine them. So this is my R sub 4, R sub 5. This is still R sub 1, R sub 2, or rather R sub 3, and R sub 1, R sub 2. There. But from here, I can also see that the combination of R sub 4 and 5 is parallel with R sub 3. So I could combine this part even further. So I could redraw it as this circuit. What I'm doing is actually I'm making the circuit more smaller. And then another one here. What is this? This is still our R sub 1, our R sub 2, but the middle resistor is actually already the combine of 3, 4, and 5. So how are we gonna solve this problem? If you'll notice, we end up with a series circuit, a single loop of circuit, considering that we must combine first the inner resistors or the resistors 3, 4, and 5 before we could evaluate the whole circuit as a series circuit. Now that we have made our circuit much simpler, we will approach the problem as what we have established a while ago. So, you begin by considering that R sub 4 and R sub 5 are in series with each other. So we will just apply the rules that we use for series circuits. To get the equivalent resistance of the two resistors R4 and 5, you just simply add the two, R sub 4 plus R sub 5, or that is 3.5 ohms plus 2.5 ohms. In total, that is 6 ohms. Next, upon getting the value of the combined resistance of R4 and R5, you can now approach the problem as if, or the circuit as if, the combined resistance of 4 and 5 is in parallel with R sub 3. So, then we follow the rules for parallel circuits. The equivalent resistance of 3, 4, and 5 is equal to their sum, the inverse of their sum. So 1 over R sub 3 must be added to the inverse of the sum of resistor 4 and 5, R sub 4, 5. Take note that we are using the value of the combined R sub 4 and 5 already because both resistors are in parallel with R sub 3. So thus, we will substitute the values 1 over 24 ohms and 1 over 6 ohms. That is equal to 5 over 24 ohms. Now remember that to get the final value, you have to get the inverse. So R sub 3, 4, and 5 is equal to 24 over 5 ohms, or that is equivalent to 4.8 ohms. Now this is only the sum of the three vectors that are series and parallel with each other, this loop. The next target is to consider the sum of R sub 3, R sub 4, and R sub 5 as if it is in series with R sub 1 and R sub 2. So, we follow the rules for series circuits. R equivalence of the whole circuit is the sum of resistor 1, resistor 2, and R sub 3, 4, 5, which is the sum of all resistors 3, 4, and 5. So you substitute the values, we get 5 ohms plus 9.2 ohms plus 4.8 ohms. In total, that is 19 ohms. Now this right here, class, is the equivalent resistance in the whole circuit. Now what if we want to find the total current in the circuit? Since we are approaching the circuit as if it is already a series circuit, and this value is obtained by downsizing the circuit into a series circuit, so we will approach as well the problem in terms of series circuit. So to get the total current in the circuit, we use the formula Ohm's law. V is equal to IR, where I is equal to V over R. What is the R here? R is the total, or rather V is the total voltage and R is the equivalent resistance. So now we just substitute the values that we know. The battery's potential difference is 9 volts. So substitute 9 volts over equivalent resistance of 19 ohms. That is equal to, let me pause the video if you want to compute. 0.4737 amperes. So this is the total current class in the whole circuit. Extension. What if we are asked for the voltage drop across this part of the circuit? Now notice, as mentioned a while ago, we approach the problem by downsizing it into a series circuit. And what we have come up is that we have combined the resistance of R3, 4, and 5. And if we want to determine the voltage across this combined resistance, we simply use the equation V is equal to IR. But the problem is, we will not use individual values of resistance 3, 4, and 5. We will use the combined values of resistance 3, 4, and 5. And the I here is the calculated value a while ago, which is 0.4737 amperes, because in a series circuit, the current is constant. Thus, no matter what is the current flowing through resistor 1, that is also the current in resistor 2, as well as in the combined resistances of 3, 4, and 5. So, we will write here, or we will use the total current value to solve for the voltage across 3, 4, and 5. That is the product of 0.4737 amperes times 4.8 ohms. Now, 4.8 is the value of the combined resistances of 3, 4, and 5. The answer is 2.27376, or approximately the voltage across the portion of the resistor 3, 4, and 5 is 2.2727 volts. Now, what about the voltage across resistor 1? The voltage across resistor 1 is equal to the current total times resistor 1. So the total current is again 0.4737 amperes times resistor 1 is 5 ohms. The answer is 2.3685, or approximately 2.37 volts. And lastly, for the voltage across resistor 2, we use again I total because the current is constant, and resistor 2 value. So that's 437 amperes times 9.2 ohms. The answer is 4.36 volts. Notice that if we add these values, this value, as well as this value, and this one, we'd come up with a number that is approximately equal to 9. So the V total must be equal to 9 volts. Let's verify that. So the voltage across 1 plus V sub 2 plus V sub 3, 4, and 5 must be equal to that. So 2.37 plus 2.27 plus 4.36 is equal to 9. We have verified our answers. The value that we calculated for the voltage is 9, which is actually the given voltage in the problem. So that is how you check your answers later on. Thank you for listening.